Welcome back to the Snap tutorial series. In this video, we'll cover the essentials of using the animation plugin within the Snap application suite. We'll guide you through creating a new animation model and navigating its various features and animation components. In addition to introducing the plugin's layout and configuration steps, we'll also show you how to connect one or more data sources to animate within the model editor. And finally, we'll demonstrate a basic example of creating an animation model linked to a completed job submission from the calculation server. Before we start, let's get to know what the animation plugin is and what the tool aims to achieve. The animation plugin for the Symbolic Nuclear Analysis package, developed by Information Systems Laboratories, provides visualization capabilities for the binary output of engineering analyses. The plugin enables the creation of animations that illustrate system responses over time, such as fluid flow, temperature changes, and pressure variations within nuclear reactors. It seamlessly integrates with various nuclear engineering codes supported by Snap, such as Trace, RELAP 5, and PARCS. This integration provides direct access to simulation data to generate accurate and informative animations. Users can enhance their animations by incorporating graphical elements known as display beans. These can range from simple geometric shapes to plant components or advanced graphing tools. Each component can be tailored to represent specific system configurations and operational states. It's important to note that Snap version 4.3.1 included several new display beans, including a pie chart, bar graph, histogram, and pebble beans, to expand the range of available visualizations. The animation plugin also enables interactive communication with a running engineering simulation. This functionality requires the engineering analysis code to explicitly support interaction with Snap. When enabled, it allows users to view calculation results in real time and adjust the simulation dynamically to achieve desired outcomes. This capability has been leveraged to transform the model editor into a simulator for operator training. In summary, the animation plugin is a powerful tool that brings nuclear system analyses to life through dynamic visualizations, thereby enhancing the comprehension and communication of complex engineering data. Let's begin with the layout of an animation model. You'll see that an animation model's layout is similar to an ordinary model apart from the values within the navigator tree. Let's direct our attention to the second item within the navigator called data sources. This element is crucial for the user to define, as it will identify the jobs loaded into the calculation server that will later be animated. Expanding the data sources tree shows two more elements: a Python data source and a standard data source. This tutorial will focus on the use of standard data sources, while Python data sources will be addressed in a separate instructional video. Animation models can include multiple data sources, enabling the comparison of various simulations. However, one data source must serve as the controller for the animation's time. This primary data source is designated as the master data source. Clicking on a data source in the navigator fills the property view with various attributes that need to be defined for configuration. The user can determine whether the source should be included in the animation, designate it as the master source, and specify the number of source runs the data source will utilize. Each run must define a URL where the data has been submitted on a calculation server. When clicking the Edit button for a desired URL, a data source selection dialog will appear where the user can select a source that has been submitted and completed within a calculation server. If the user so chooses, a minimum and maximum time can be included in the data available from this data source. This value will be used to narrow the data available from the calculation server. In addition to the general properties provided, the user also has access to the ext data channel name patterns. This group contains a set of patterns used to generate channel names from volume IDs for the display beans connected to this data source. The resulting channels can then be utilized with color maps to display parameters such as liquid temperature, quality, and more, based on the bean's selected volume ID. This enables ext data jobs that adhere to a proper naming convention to seamlessly integrate with display beans using volume IDs, similar to how Trace, Relap 5, and Melkor jobs function. Patterns can be entered for liquid, vapor, and saturation temperature, as well as pressure, void fraction, and quality. Note that color maps of the type fluid condition require only 4 of the following patterns: liquid temperature, vapor temperature, saturation temperature, and void fraction. Note that these patterns are only used when an experimental data job is selected for this data source. A key feature of the Animation plugin is its capability to handle sequence data sources. With this function, playback begins at the start time of the first job, using its data for the initial animation. As playback reaches the start time of the next job, it automatically switches to that job, reinitializing all display beans to animate the new data. This process continues sequentially, transitioning smoothly from one job to the next as their start times are reached. Currently, the Animation plugin allows up to 4 source runs per data source. Let's turn our attention to the Color Maps element within the Navigator. This feature allows users to define a range of colors and associate them with a user-defined range of values, which are then used for display bean animation. Display beans can either reference one or more plot data channels directly or specify a volume ID. The channel or volume information is passed to the color map to determine the color of the bean for the current time value. This allows the user to visualize the state of many plot values simultaneously. The properties of a color map depend on its selected color map type. Each type has its own distinct set of properties. Changing the color map type will alter the displayed properties in beans using that map. For example, the segments defined for the void fraction type are independent of those for the liquid temperature type. Switching between types can change the data channel or value range being visualized in all the display beans that use the current color map. Typically, this only affects display beans that are using volume numbers. When a new color map is created, it starts out as a generic color map. This color map type allows minimum and maximum values to be specified as well as the engineering units for these values. It's important to note that the engineering units must be defined for proper unit conversion. The generic color map type is particularly well suited for beans utilizing the channel ID property. For volume ID beans to function with a generic color map, the color map must include defined channel name patterns to convert a volume ID into a channel name. Generic color maps are especially useful in scenarios that require extensive customization. Moving on from the generic color map, we come to the temperature, pressure, quality, and void fraction color map types. These are distinct from the generic color map and are tailored for specific applications. They work with beans that use either a volume ID or a data channel. For these types, the minimum and maximum values, along with assigned colors, define how each bean's color is rendered. When beans use a volume ID, the animation module loads data from a graphics file to identify the channel displayed. For instance, if a user wishes to visualize the behavior of the void fraction in a pipe cell, they would begin by creating a pipe segment. This is done by using the drop-down button on the insertion tool within the view window, navigating to plant components, and selecting pipe segment from the available elements. Once the pipe segment is created, the property view is populated with the segment's properties, where the data source and color map are defined to source data and dictate the color scheme for the current data channel. The volume ID is used to automatically identify data channels based on the color map type. Next, we will discuss the generic 2D color map, which introduces gradients along both the X and Y axis, enabling more advanced visualization. This color map uses the Y-axis data values to determine color interpolation across multiple segments. The X-axis data values are used to modify the Y-axis gradient, transitioning it to a single fixed color. The properties for the generic 2D color map are accessible through the configuration dialog at the bottom of the property view. This dialog is divided into 2 main sections, the Y direction tab and the X direction tab, each offering specific controls for customizing the gradient. In the Y direction tab, you can define how the color gradient changes along the Y-axis. This includes options like using single color segments defined by the range start and range end properties, or to enable multiple ranges, allowing the user to break the Y-axis into several color segments. The X Direction tab provides controls for adjusting the color gradient along the X-axis. Here the user can set the gradient to transition to a fixed color based on the range defined by the range limit minimum and range limit maximum properties. Some additional features in the dialog include out-of-range colors, which set the display for data points outside the defined ranges, engineering units, ensuring proper unit conversion between SI and British, and channel name patterns to specify how data channels are identified from a volume ID. Now that we covered most of the categories of the animation model in the navigation view, let's look at the animation playback toolbar provided above the view window in the model editor. The playback controls are located in the animation toolbar and provide a simple interface for navigating and controlling your animation. Let's go over each button and its function. To enable the playback animation toolbar, you must click the Connect Data Sources button provided on the far left of the available button selection. This links the animation to the currently defined data sources, enabling it to retrieve the necessary data for playback. Once connected, the button changes to a disconnect data source, enabling you to sever the link to the data source if necessary. It's important to note that only one animation model can be connected to a data source at a single point in time. The next button we'll talk about is the Analysis Time button that is used for the configuration of time-related settings. Here you can seek a specific time in the calculation by entering the desired value, set the playback to be proportional to real time, adjust the skip forward and back steps to define how many time steps are skipped when using the skip forward or skip backward buttons, or modify other time-related settings to tailor the animation to your specific needs. After configuring time-related settings, let's move on to the controls for managing playback on the animation. First, we have the Refresh button, which updates the view with data from the current time step. The Rewind and Fast Forward buttons will take the animation back to the very first or last available time value, respectively. The Skip Backward and Forward buttons allow the animation to move back and forth by a fixed number of steps defined in the previously stated analysis dialog. The Play button starts the animation and changes into a Pause button, which in turn pauses the animation being played. The Stop Animation button halts and resets the animation. Note that this button is only active while the animation is playing and when the playback reaches the final time step. In addition to the playback control buttons, we have the timeline bar that represents the entire duration of the animation. Using the standpipe model included in the link below, submit the interactive stream within the available job streams. Once the job has been completed, let's create a new animation model. Navigate to the data sources and click on the master data source. Open the source run URL dialog and select the transient step of the recently submitted interactive stream. Create an axial plot by navigating to the View Windows drop-down option and select the axial plot from the available graphs. Open the Plot Data dialog in the Display Beans property view, create 20 values, and paste in the entries within the data.txt file supplied in the link. Connect the data source using the Connect Data Source button. Using the Analysis Time dialog, set the playback to be proportional to real time and set the value to 10.0 and press OK. Press play and watch as the animation begins to track the void fraction within the transient event. This covers the basics for working with the animation plugin in Snap. Thanks for watching.